All right, 7 o'clock. Let's get started. Just an announcement about midterm. It's coming up in a month's time, so you should be prepared now. It's on a Saturday. The scope is lecture 1 to lecture 8, then recitation number 1 to number 5, tutorial number 1 to number 5. All the concepts in lecture 7 and 8 are included. As usual, this is an open book test. I will put the page 1 of the paper here subsequently in the coming days or weeks. Midterm FAQ, this one, I will see whether we need to do it anymore or not. All right, more importantly, this re-exam, it's on the 4th of April. This is the standard that we do. Basically, we do the actual test, and if for whatever reasons, there are two here, if you have a valid MC for that day, on the actual day, you can submit that to. We would like you take the 4th of April re-exam. I should say that re-exam is usually harder than the actual exam. But anyhow, it depends on the individual, how prepared you are also. Okay, so you have to submit your MC before 12 noon by emails to me. Okay, so this is one situation. The second situation is that you do have official duty while you're still in NS. In that case, you have to have a letter sent to me by your signed by your captain or above before 21st of March, which is about a week before that, for verification to confirm the right to take the re-exam also. Right, and we will need you to submit the original on that day also. All right, so this is the hope that all of you can take the actual test to be fair to all. And otherwise, the re-exam is going to be slightly different, but it all depends on how you are. Okay, any questions about the midterm? You can type it out in the chat box if you don't want to say it. All right, if not, then I move on to our actual review for today. That is our review on lecture 8. All right, last week we reviewed lecture 7. Pretty much it is you learn things about um, algorithm until lecture 6 you have the higher order function. And starting from lecture 7, we have the data abstraction. Basically, this part writing program. This part is now on the how to make use of your ingredient, your data to write better program. Okay, so lecture 7 it's using Tupper. Lecture 8 it's also Tupper but more. Right, in the lecture 8 you will see that now besides Tupper, list and string which you encounter very early day of this course, now we will have dictionary and set in here as well. As you will see that in all the subsequent lectures, somehow some of this stuff are being used. For example, tuple is used in this lecture as a representation for tree. But it is by no means that tree can only be represented as tuple. Okay? Actually, tree could be represented with list also if you want to. But of course, it doesn't make sense to represent tree with a dictionary. Okay, dictionary is, you will see the use of dictionary in dynamic programming. All right, so each of these stuff, it's of certain purpose. All right, so why do we work with sequence or collection? So sequence means that is order set. Collection means is order or unordered. It include both. Okay, so tuple, list, and string. In some sense, string we'll just take it as individual character. We will not list it down here. And in this listing dictionary, it's stated as unordered. Actually, after 3.6, actually, dictionary is ordered, as you will see. All right. Anyhow, this kind of stuff, which is implementation dependent, you do not have to worry too much. As we need, we will spell it out. But in this course, we are using Python 3.11. All right. So most of the time, so this particular, I should have written this as ordered. Okay. So this should be ordered. All right, and why do we work with sequence or collections? All right, sequence is ordered, collection is unordered. It is because here's the statement I should give it to you. All right. You know that the power of computer program is on looping. All right. And looping means iteration or recursion. All right. And the computer can do it very fast at each loop. If you without any loop, if you look at the program without any looping, it will be just simply sequence of statements. And I think such kind of program will have limited use. Basically, it's one statement after another. And in such case, most likely you can hard code your solutions in some way, and you need not actually have a computer in some sense. All right. The power comes from array. This is a generic word. In other programming languages, we use the word array to mean various this kind of stuff. Array usually will mean list kind of stuff. All right. Array is a generic name in the sense that now variable it's only one name. As you can also by now, by the time that you do your programming, you always scratch your head what names to give to this variable. Okay, and array is actually a variable with different indices. Basically, you can tag a number to it. For example, if I have to call each of you, then I will have all these various Isaac Lam, like James Tan, and so on, Brian Chung, and so on. Instead, if I call you student one, student two, student three, or I even use students' index number, and so on, then my program will be easier to do. I can do a loop with all these student bracket I, and I can get through. So that is the power of computer program. It allows you to use array, which is any one of these guys, and with index. And all these guys have some indexes. So tuple has index, is represented by parentheses. List is a square bracket, and dictionary it's the colon. So set is like that. So instead of but this set you probably cannot take which order because it's unordered. So for tuple and list, you can use index 1, 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, and so on. Dictionary is an interesting one. It allows you to index it with some arbitrary string or tuple and so on. So dictionary become some sort of powerful, but you may not need it all the time. Sometimes, most of the time, tuple or list should be enough. Okay. So that is the power when you look carefully all the program that you are dealing with, all the meaningful program that you're dealing with, they will have some form of looping. And they have some form of looping. That means that you have to understand what is the meaning of the program through the looping. And the looping usually contribute to the time complexity, the time or the space complexity, because this is the place where it keep iterating and it keep changing things. All right, and another note that you should know is that sequences, this kind of stuff or collection, they are subject to uh, only these five types of thing. I mentioned that in the higher order function. Higher order function deal with big data. When you're dealing with big data, you cannot run away from five things. You are doing either searching thing in the big data, or you're sorting thing in the big data, sorting the big data into some order to help you for other purposes, or you're doing mapping to take each data and do some calculation, or you do filtering to take away some of the data that you do not want, or you're doing aggregating to take some statistics, average or mean or medium and so on. All right, so you cannot run away from all these things. As you will see also in our various midterm assessments, they are all centered around these five types of things. Okay, and the next question is which sequence collection is better for use? So here it's my kind of answer. You can dispute it or you can challenge it. All right, my kind of answer is that it depends on the frequency of each type of operation. Now, when you're dealing with big data, you cannot run away from this kind of stuff. Basically, when you do mapping, you're doing some calculation. Filtering, you're doing some of this stuff. So, more commonly, we know that the kind of operations are updating, searching, deleting or adding or some kind of calculation to the data. So how the data is stored, it will affect the way that you do the updating, the searching, or the deleting, or the adding, all right, and other calculation. So we will want to know roughly what kind of frequency of each of these type of operation. For example, if you do adding to tuple, you got no choice but to destroy the original tuple and create a new one. So that costs you the length of the number of items in the tuple. That is no good if this kind of addition or adding happen often. All right, that is the frequency of happening. Instead, then you should be using list. Okay. All right. So you always wanted to have a data structure, which means either tuple, list, or dictionary or set that are catered towards giving you operation that frequently happen. All right. But this kind of thing, the frequency, it's hard to know in practice. So this is in theory, we should be looking at a frequency, but usually there are certain common sense that we play with, or you do some guesstimation work, or you do some simulation. Simulation means that you try to uh, do some kind of there are always established things in the simulation world that you can simulate the arrival of customer or the departure of customer, the service time and so on, all this queuing theory. Okay, so frequency, it's in theory we should be interested in, but in practice, sometimes people will just have to do some guesstimation work. All right, and it's also possible that data structure can be done in data abstraction, as you will see in lecture 10. All right, meaning that you don't really care which of these guy is the actual implementation for this thing. It's being abstracted out for another level. This is a common thing in computer science also. All right, it builds things layer by layer. The layer that you're dealing with may not need to worry about the underlying data structure because it's being abstracted out for you. And so you only see the operations, and the operations are adding, deleting, and so on, but you just call it, and the underlying library will do the job. And because of that, so if you do design something like that, and you can actually replace the underlying layer once you found that there will be better way to do it in some sense. For example, in lecture 10, you're going to see that one way of representing complex number, and you can have another way of representing complex number, and the operations are all the same. You can switch between or among, if you have more than two, all the different types of representations without affecting the actual usage of it. For example, another good example is your picture language. The picture language is a layer on top of things below. And so if you do whatever you changes to the lower layer, it doesn't affect the operation on the upper layer except for the time and space complexity, right? But it will still meet the objective of doing something. You want to show this, you will show it. You want to do iteration of this thing, you will do the iteration of these things. But the underlying data structure could be list, could be tuple, could be dictionary, whatever. But you don't care. Okay, so this is data abstraction. You experience that in lecture 10. All right. So this is just a statement to repeat what is said there. By the way, in our assessment, just for example, in our this recitation, there is all this usage of this question about course question number 4. This is pretty dumb in a way that using Tupper, but because this recitation is on Tupper, so you will take it that you will use with Tupper. We will work with Tupper, but actually you should not lah, because a better way to do this will be in a file structure or even list will be better than this. All right. But in our assessment, meaning that in midterm or in tests or in practical exam, whatever, you will be forced to use certain data structure, data type for our purpose of assessing you on that particular data structure. So You should not question it. If you're asked to use it, you just use it. Okay, but it may not be logical in the real life situation. Okay, but it's only for our purpose of assessing you. Okay. As you will know, actually Chinese has a very interesting saying that uh, you are born for a purpose. Okay, so there is a phrase is those of you who study Chinese, you will know 天生我材必有用. All right, and so yeah, whatever it is, whichever type it is, it's actually some kind of comparisons, the similarity, the differences, and the options that are available to you. And you actually should learn about this thing already last week. Similarity, Tupper and List are kind of similar that they are both ordered. All right. They allow duplicated members. Yeah? You see these two already the same, except that Tupper is immutable, List is mutable. Okay. So there are similarity and there are also difference, and you choose which one. And how you choose it depends on, for example, frequency, which one you are going to likely or more oftenly needed, and in terms of time and space complexity. And then you will choose between the two of them. Okay. All right. So we will need to know how to work with each of them. So last week we probably show you a little bit the tuple, the list and dictionary and the set. And you also need to know how to work with each of them passing on to function. We talk about Python passing by object reference and not the other way of passing by reference. And then particularly, of course, passing to function, there's a particular danger here with recursion that you need to watch out. So these are the 3 points that usually whenever you learn a new data type or data structure, you should take a look at this. All right, so I want to show you a little bit with some of these just to reinforce your understanding. So here is I can provide this code to you after tomorrow. I will post it in the link to the review. Okay, let's see this. All right, let me just quickly go through it. First, it's got to do with tuple. So here's the tuple, 1, 2, 3, 4, 5. You print tuple ID, and you saw this thing. That means the address of the tuple. All right, so this is some location in the memory. And if you print out one by one, tuple it's ordered. So you 1, 2, 3, 4, 5. You just print out in that manner. Okay. Now, if you change this tuple to slightly different, it's 1 plus to 6. All right, 5 and a 6. So actually, this T and this T are the same, except that this guy has an extra 6. All right, you may be tempted to write things like, all right, T is equal to T plus uh, 6. This should still work. Let me see. Okay. Let's comment out this guy. Just use this first, if it allow me to do it. Okay, it does allow me. Okay, now here. So this tuple is at this location. Now we make it into T plus 6, comma. So you have a 6. Sorry, I make a mistake. I don't want to do 2 times. Okay, I'm here. So this is my location is 4464. I add 1 6, so there's a 6 here. Oh, this is not a string. I should have added a string. Anyway, tuple ID. So you can see that this ID actually is different from this ID. It means that the beginning of this guy, it's the different from it was before. All right, if you want to verify this, actually you can edit this code and you can put something here. You can S is equal to T, then you will have okay, here I have a S and a T together. Now, if I do this, you see that this was remain and this one has changed. This guy was at 5392 and this guy is now at 1680. Okay, so it is to tell you that Tupper it's immutable. Whatever you do to it, you will create a new guy. Okay, so here it is. Next, we see the list. Okay, whatever I'm doing here, it should be something in your learning journey also. All right, and I use quite a bit of this Python tutor to help myself also to understand what are all these pointer and box things. And I set question based on this stuff too. All right, this is the list. So list is this. And if we print out the list, now no surprise. While list is ordered. Now you append a list, you get a 6 there. All right, so uh, you see that it's still the same location. Okay, so and here actually you should also watch out. So for example, you may think that this is 6 or a list is a 6 plus a list. Okay, so if you do this, oh, list plus 6, let's see what happens. Here we have 1, 2, 3, 4, 5, and this is going to give me a 6. My list was here. I mean, this 65248 is here. So if I do this, then I print this list. I got a different location. All right. So actually, it doesn't know that this is this. So you have to watch out. This is a very strange thing. But anyway, let me do another one, another version for you to see. What about this one? Right here. All right. I have my 1, 2, 3, 4, 5. My list is at this location. I add 1. Is there. Print list. And this time, you see that they are the same. Okay. So this is a very unusual in some sense. This is very implementation development dependent. Another thing you can notice is that if I try 3.6 on the same code over here, and my memory location is 6184. Just now, after we did it for version 3.11, we got the same location, right? This time, this time is the same location also. Plus list. Okay, did we get the same location? Okay, let's try. So I'm a little bit apprehensive about some of these operation. It looks very similar, but yet it's try not to do this. You don't want to do it. Okay, so the two versions are the same, but sometimes the versions are different, can result in different things. Okay, so here it seems to be the same. All right, so just watch out for this. This and this, or at least this one, it's not going to be the same. 11. Okay, let's try this one. Maybe this is the one. Yeah. Okay. This time is different. Let's try the 3.11, 3.6. Okay, so you may have to try it yourself to see. Anyhow, this kind of stuff which is implementation dependent, we should not be expected to know for the midterm or whatever assessment that we have. See, now it's different. So the 3.6 give you different answer. Okay, so you should be using this kind of thing more proper. That's the message that I want to share with you. Okay, so this is the proper one. That both versions should be the same. All right, so that is the list. And next is the set. The set is unordered as shown here. So you see this A, AB, AC, and D. So you see there's no particular, you can't tell. They just put it into the box for you to see. Okay. And you want to see the address. Let's see. Now, you want to list out the object in the set. You put it in as A, AB, AC, and D. So you should not expect that whatever you're going to get out is going to be in this order. So the first one you get is actually AD. Maybe this guy. Okay, it's not the first guy that you get. The second guy you get is AC. Which is this one, not even the A. The next one is A. Okay. Then the last one is the D. All right. So this is kind of you should expect because it's a set. Set has no order. Next, if you add something to the set, which means that DD is added, you get the DD in there, and you you want to check the address. The address was 2632. It should be the same. 2632. So it's the same location. But if you now list out the item, you used to list it out A, B, A, C, A, and D. Now what you see, you got AC instead of AB. You got what's the next one? D instead of then you got AB. So we mess up all the order now. All right. So don't expect to get the same order for set after you added something. Okay. Next it's a dictionary. Dictionary, this is an interesting keyword. The dictionary is like array with index, not necessarily number. Okay, so this is a message that you should remember. Basically, so the index here is 44. The index here is 11. The index here is 23299. The index here is 3. They are not, and the value is 1, 2, 3, 4 string. Okay. So as I told you just now, after Python 3.6, so this guy is an order set. So this is ordered. So you give me 44, 11, 2993, you will get 44, 11, 2993 in the order. Okay. How this is implemented, this is a little bit tricky because a dictionary, it's actually a hash map. A hash map has a lot of empty space, and you will see that in another course. And as a result, all these guys are actually not contiguous as shown here. They could be far apart. It's just that they are listed contiguously according to the order that you input it. All right, so now the location is 9472. So this location should not change, basically it's there. All right, you see, you're getting out 44, then 11. This one you can expect in that order. All right, now the value is also 1, 2, 3, 4. All right, 1, 2, 3. Okay, so now you add another guy, 88, you will just be added at the last. Okay, so no change to the previous one. So after adding, there is no change to the address. So whatever you have 9472, you will remain as 9472. Okay. And the order still remain the same, meaning that you will get 44, 11, 299, 388. Okay. And the value will be 1, 2, 3, 4, 8 as expected. All right. Oh, sorry. I wanted to be here. Okay, yeah, here. So 299 is here. You pop it up. So you destroy one guy. Actually, unlike the case of a tupper, you destroy something, you're actually creating a new one. This one, no. This one is still the same guy. So you pop it out, you get 299 was a 3, right? 299 was a 3, yeah. So now you pop it out, the address still remain the same, 9472. All right, 9472. As for the value, the guy just pop up and the rest of them just maintain the same order. So you will get back the same guy. Okay. And that's it. All right. So these are the kind of differences or similarity that you have to find out yourself. Oh, I was using 3.6. It shouldn't be any different for 3.11. Okay. So that is just a demo to show you that you have to watch out for some of this stuff. Don't try to rely on ordering for the set, and you can bet on the ordering for the dictionary, even though they shown it in this manner, but they are not in this fashion. And there are two website, two link that you should see. The time complexity. This one is it says that they don't have money to maintain it anymore, so this guy will be gone soon. But I used to use this one. The same you can use it. This one. This one has more pages that you have to flip to get the answer. Whereas this one I can see in one glance. All right. And you saw in the posting, and some of these, why it is so, it is basically a trade-off of time and space, right? So there's no free lunch. If you get minimum and maximum, in this case, is O of n, is linear, but you can make it into O1 if you use min and max often, okay? But once you make it O1, you will have to pay for other places inserting. You inserting, you will have to watch out to check whether this guy inserted is the new min or the new max or not. And also, when you're doing deletion, then you are even more trouble also because you are deleting a guy and that guy may be a min or may be a max. So you may have to recalculate it and so on. So by changing one, you will change some other as well. All right, so this is what it is being implemented in the current Python, and we will take it as is. But you should know by now that all these are not cast on stone. It can change in the sense that if you give me additional data storage or what we call metadata, all right, metadata is not the actual data but the description of other data, then you can actually be cheaper in some of the operation. All right. Okay. Any questions so far? All right. There is a note here that you should watch out. That is in this particular lecture, some of this code, because it's a tree, tree is it's already non-linear. Linear means it's one line, straight line, one after another. Tree, it looks like branches. It looks like branches like that. And as such, the code can be very complicated. Okay, particularly if you look at this guy, you should pay attention to how to study this guy. I think it's 52. Oh, here. All right, so this is the init function with a map thing. The map is the system map or our own map. You can do either one. And so you should study some of this code to understand why. So you see that in this code, actually the recursion here is 3 scale. It's this one. You can try changing this to the scale function. You will see that it didn't work. Okay. So this is a more complicated codes that you should try to understand to beef up your understanding of things. Okay, I have a little bit more time that I will fill up this. Basically, what you're doing now are these are the things that people told you. All right, primitive data type. Let's just like the primitive algorithm in the picture language. All right, they allowed you to turn 90 degree, or turn left 90 degree, turn right 90 degree. Actually, you don't need to turn right because once you know the turn left, you can always turn 3 times. It's the same as turn right, and so on. So there is a set of basic functions that we provided you for picture language. It is the same for data abstraction or for data. The various type of data given to you, it's primitive. It's like tuple, list, dictionary, and set. Okay. And but these are not the enough in sometime in application. So what it's given to you, like just the functional abstraction, we can actually get derived function. So from the turn left, you can write another one to turn right, okay, by applying it 3 times, all right, or you whatever. There are many of these examples. So basically, you can derive your data type from the basic one. It's coming from mix and match. That means that you may be taking some tuple, some list, and make it into your own. Okay, and why you do that? It's because of applications. So these 3 columns is something which you should realize. All right, because of some application that because there are some frequency issues that I want to use list because I updating the value very often. On the other hand, because I want to use tuple, because I want to use it as a key in the dictionary, which list cannot be done. All right, tuple can do it. So I may mix and match things. I will keep both the tuple and the list in this application or whatever. Okay, so what I wanted to tell you a few other points are here. All right, so the tuple is a linear structure, unlike tree. Okay, that's why we have the derived data structure for tree coming from tuple of tuples. Okay, and searching is O of n time, where n is the size of adding is also O of n time, modifying is O of n time, where n is the number of elements in the current list. There's one more point here can be used for hashing. That means key for dictionary. Okay. All right, and this is well, list cannot be used for dictionary. Okay. All right, so that it's tuple. You have to recognize it, and if you want to use it for dictionary, you have to have tuple. You cannot use list. On the other hand, list you have the searching it's on time. Why? Oh, because you may be unlucky that the guy that you're looking for is in the middle of the list. You got no choice but to find until the middle, which is halfway. O of n divided by 2 is O of n. Adding is O of n or O of 1, depending if it's O of 1 means you are appending it. So it's at the end, then it's O of 1. Otherwise, it's O of n. On the other hand, I must say that list, as you study, you will see that you can have many kind of lists. I could have created another list here that it's actually double linked list, two-headed, two-sided. You can go forward and backward, all right, at ease. And then you are able to do adding in O1 time also. But on the other hand, they will affect other things. Okay. So modification, it's O1 when the position is known. Actually, this is also a little bit tricky. Even the position is known if the list is not homogeneous, meaning that they are all different types. I don't know how the calculations of the address is working out, but maybe the Python system has a way to pointer and so on, and it does it with O1. And the min and max implementation, I had a posting in the forum earlier or last week or so or earlier. And you can see that min and max can actually be achieved with not necessarily min and max is O of n for list, but you can do it with O of 1 if you want to by providing metadata, which is the min and the max. but then you have to pay the price to, when you delete someone, you have to make sure you check through, or when you insert someone, you may have to check through. All right, so it's no free lunch. Basically, you have to understand this. Just that you can see most of this stuff are implementation dependent. All right, dictionary is an interesting one in the sense that it's not available in most of the languages that I learned previously. Basically, you have to create it yourself if you want a dictionary. All right, it is not hard to create it once you know hashing. Um, just that is the choice of the size of the storage you need to use, and there are mechanisms for you to make good your implementation. Like if there are too many collisions due to keys and map to the same place, you no longer be able to do all one searching. In that case, you have to rehash, and then you will have to doubling or this kind of stuff that you can then make it into good again. Right? Basically, that it's what all these things. All right, Python 3.6 onward dictionary is ordered, so I've changed my slide a little bit. So you saw just now the listing of the items in the dictionary is in the order that you add in. For that to happen, you actually must have a link from one item to the next item. But that also have implications. So it somehow they are all right. So if there is no such a link, here is stated there, and then the kind of listing will take you O of n time, where n in this case is the size of the dictionary. All right. So all these are pretty tricky. And sometimes we sweep everything under the carpet, but you have to be careful in knowing that opening up the hook is to help you to be able to see clearer what are things. And many of this stuff really nowadays you take it for granted because computer is so fast that we pretty much and computer is so fast and so much so storage is so free, it's so cheap and so on. But actually, no matter how cheap or how fast, there's still a limit, and we cannot go beyond the speed of light and so on. And so there are all these limits still, and still there are computation. You're not careful enough, you're going to take years or decades if you're not careful with the implementation. All right, so it's still good to be able to know behind the scene in a way what actually happened. Okay. The last but not the least is set. All this set it's also kind of interesting. It it's actually you saw it. It has no order, but it's actually also a powerful thing. There's this thing called Union Find. You can Google it to find it. Basically, allow you to check who is the boss for a particular tribe or who is the chief in a tribe. Or in the case of the most of this stuff come along because of compilation. A long time ago, Python is an interpretive language. When I say compile, for example, Java that we're going to encounter, this is actually a very interesting data structure. This is already in the derived data type. I should show you some of the stuff. Okay, complex number. It's lecture 10 is it's multiple representation. So you can say that it uses all the different types, and it's called a derived data type. Q it's not directly. You can use list. Of course, if you use Tupper to do Q, then it's a little bit the no good because it is costly. Because first in first out, you want to be able to take it things and remove things, put things, and so on. Likewise for stack, it's better that you use list. Okay. In the case of tree in lecture 8, we use tuple of tuple. There could be possibly other ways, like list. If you do have to change the entry in the tree. For example, here, most of this stuff are not changing except for the leaves. So, okay, so you can use tuple of tuple, whereas the bottom, they are all just numbers. Okay, but on the other hand, if you this kind of tree, it's the content is not inside the non-leaf, but at the leaf. These are the leaf. Leaf means that they are no longer any more branches out. These are the trunk in a way. In the trunk, there's no value. They are just pointer. Okay, so the pointer never changed, and using a tuple to tuple, it's good enough. All right, but you should try to play with this thing also with list of lists, and then you will see that some of the stuff, sometimes you may be able to do away with it with some of these creation of things. Tree so there are all the various kind of tree, the priority queue, the AVL tree, and whatever trees in computer science, they are mostly balanced. Okay, balance. The word balance, it's always come about because they are, the two things that you don't want a lopsided tree that you become a linear. It's no longer a tree, but just like a stick going straight up all the way, and you will not be able to gain the advantage of tree, which is always a log n complexity in tree. Okay, for example, where n is the number of leaves. Basically, you can reach the bottom of the tree by log n branches. If you're not careful, you will have to then the tree will degenerate into a linked list, a linear list. Okay, if not careful, just a list, a straight list. Okay, a straight line tree is useless. Okay, this is the derived data type. So these are the basic, these are derived, and there are some various application. Just list out some of them here. In lecture 4, recitation number 4, the question is asking about Tupper, but actually it's not really suitable. But following that, in the case of assessment, we got no choice but to follow our instruction. So we will do that by using only Tupper. I think that's all I have. So basically, you have the 3 columns based on application, based on what you're given in the primitive data type, you study, and you are likely to be able to create a new derived data type by combining things. All right. For example, in this, I would say that for example, in here, if you want to create a list, having this want to make minimum to be 0 or 1 because you always get the minimum always, then you are creating a derived data type by packing a value which is a meta value into this list. So this list is just you will see this as maybe a list of lists. You will be the minimum value, the maximum value, and the actual list is here. So this is already a derived data type. Okay, in a way that to achieve mean and max in linear time, I have to pack all these guys into part of the list. The actual list is just here. Okay, so I am creating a derived data type to suit my application. Should my application needing a lot of mean and max. Okay. All right, I'm done with this review. Basically, I wanted to impress upon you on the knowing the similarity, the differences, and the options available to you. And the option means that you have derived data type. And it based on the application, and the application based on you have to check what are the frequencies of things that you needed to do for that application, and then you will design or pick the right data type, data structure. Okay, I should stop here. Anything you want to ask, or we can take a break of 10 minutes. Anything, or you give me a check if you are okay. Okay. Right. There used to be why is the Python version will change how the list operators work? Oh, there are two questions in the chat box. They are all direct message to me, so you don't see them. Number one, why is the Python version will change how the list operators work? Okay, whenever you see a Python version, it means that this 3.6, the 6 is a minor number, so 3 is the major, so there will be Python 2 point something. From 2 to 3, there's a big change, so the syntax could change. So for example, I remember used to be, print used to be, print used to be like that, right? But now cannot. Print must be like that. That is a major change. Okay, these are in a way major change. Number two, in a small change, this could mean that some functions, the actual implementation has changed. Therefore, for example, they may have decided that now I want to represent my list with the minimum and maximum. So I change so that I can change the complexity because there are a lot of requests from people using Python. Okay, so it all be driven by usage. So, and also how loud you can shout in a way in this community. And then people will do or not do accordingly. All right, there are sometimes votes, and then the developers of this will have to decide what to do or wanting to do or don't want to do. So all the different Python versions will change the way that the operator work, and as a result, the complexity may change. All right, so that's one question. The second question is someone asking about CS1010X versus CS1010E. I believe the E means engineering, right? The so CS1010E will have the normal schedule, I guess. If it is done in semester one, that will be 4 months. CS1010X it's much longer. Of course, if you are problem with this course, you can just hold on to it and finish it still, and you can ignore it basically, and you can then redo CS1010E. Okay, of course, by then you should be better off not starting 1010E from fresh. Okay, you will be starting with some understanding in computational thinking. Of course, all these are up to you. There's no, it's you pay the fee, school fee for the course. That's mainly the cost. Otherwise, it's learning. We emphasize more on actual learning than the grade. Yeah, the grade you can throw it away basically if you don't get a good grade by the end of this course, and you can declare whether you want to keep it or you want to throw it away. Your senior will know this very well. Okay, any other question? Uh, if I do, if I do 10x, do I have to redo 10 for my appropriate? No, 10x is a replacement as far as I know for all the other CS1010. Okay, and if you want to ascertain that, you should check with the undergraduate office. As far as I know, 1010X is designed to benefit, at least as a welfare in a way, to NS men. Basically, you can take it earlier than many other people. And therefore, by the time you enter NUS, you have this already done. And you can use it as a prerequisite to all the other advanced courses. Okay, so once you do 1010X, you likely not need to do 1010 of whatever version. But there could be exception. I do not know because of the language. For example, the IS department, the information systems and data analytic department, they what do they do? They use Java or something. I cannot remember, but our undergraduate office will be able to answer you. Okay. Yeah. So we take a break of 5 minutes, then we come back. I rearrange my screen. Okay, there's a question about sorting algorithm is stable or not. We'll get to sorting in the coming lecture, lecture 9, I think. Okay, 8 o'clock. Let's get started. Today it's recitation number 4. It's on data abstraction. Basically, the various things about the tupper, the dictionary, set, list, and so on you saw just now. To reinforce your understanding, maybe I can try to do a little bit more. Okay, we saw this one. Okay, here is another one. So this is the various things which you actually were, in some sense, repeating what I said just now. Okay, but anyhow, let me go through it because just now the review is not a compulsory lessons. Okay, so if you have a tuple like this, the length. So maybe I can try some of you. Brian Chung.
Yes.
Brian.
Hello, hello,
Yes.
bro.
Okay. Yeah. Can hear you louder. All right.
Yes. Hello.
Print length of T. What is this?
Four.
4. Okay. S is equal to T. So S and T are joining there. The address of S and the address of T, are they the same?
Yes.
Yes. ID of S, so it should be the same as ID of T. Okay. Now, T equal to T plus this. What do you think? We went
It
through this.
will point to another tuple.
Yeah, you point to another tuple. Well, that tuple will be what?
It's a new one, a completely
New
new
one
one.
of
Yeah.
what? What is the content?
This whole tuple plus another four behind.
Okay. And you copy this guy also.
Mm.
Okay. And a 4 behind. Good. ID of T, now, of course, is not going to be the same, right? So they are different now. ID of T2,
Uh, I think it's
T2,
this. Is it the same?
T2, this one.
Yeah.
Okay, which means it's this guy, right? 2944. ID of S2, this one.
Is
Should
it
be
the
the
same?
same. Yeah. So they are the same. True. S and its ID is this. Okay, S is this content, and T is this content. Uh, they both have these two the same. ID of S and ID of false. Okay. Next, now list. Let's try another guy. Xavier Quack.
Yes, bro.
Hi. So K equal to this. This is a list. M equal to K. M is another guy. Just pointing to the same place. K append 5. What happened? K is here. Append 5. This guy appended with the 5. At the back?
Yeah, everyone, it will be at the back.
Oh, yeah, okay. At the back, and now you see that this guy K and M are actually pointing to this. So there's a side effect to M that it get also the 5. correct?
Yeah.
Okay. All right. So the address of M and K still remains the same. ID of M before adding 4. What is this? Before adding 4. Okay. The 4 is to be added here. So M equal to M plus 4. What happened to this? So the 4 is going to be here. Let's see. No. So the M equal to M plus 4, it actually means copying this whole thing and a 4 there. All right, so this is the danger of the list allowed you to do this, and this is different from M dot append 4. Okay, so you actually make a copy. So now M and K are separated. They are not the same. And the ID of K is just that. What about this one? K plus equal to 4. So these are the things that I tried just now also in the review. So let's quickly go through it. So this is K. It's here. I want to plus a 4. So the ID before it's 3536, huh? So let's see. The 4 is there. And the ID of after adding is what? Oh, it still remain the same. Okay, so this guy happened to be the same as K dot append that number. Okay, but you try not to write this kind of stuff, huh? If you want a pen, you just put a pen. Oh, that this is more dangerous to tell, because in the case of this, you know that already the tuple has changed. All right, so actually tuple and list are quite different here already. Next, the IM they are different, and the 3 and 3, but they happen to be the same still. Okay, they are still the same. Okay, so this is the some of these things and the revision of what we did just now. All right, in the case of function, okay, so now here is there's a version different, 3.6 versus 3.11. All right, so this is let's see, this is a full. My tuple is 345. I pass my tuple into here. So both T actually pointing to 345. If now my T equal to 1, 2, 3, okay, that means that I change this guy to 1, 2, 3, so this guy will be taken away and 1, 2, 3 will come. All right. And when I return T, but return T never pass to anyone, so it just return, but nobody use it. When you print T, it still remain 3, 4, 5. Now, let's try. This time we try to be funny to make 3, 4, 5, 3, 4, 5. Okay, let's see. All right, so 3, 4, 5, 3, 4, 5, and what happened to this? Under they are the same. Okay, now when you do this, change this to Python 6, 3.6. Let's see. Look, there's a new tuple. All right, so this is implementation dependent. And version 3.6 to version 3.11 has, maybe you can call this an improvement, because the 3.11 knew that 345 is the same as the original one, therefore it didn't make a copy, it just retain it. All right, so but anyhow, this is tricky for us. So there's some implication when you're using this kind of thing, when they are implementation dependent. All right, so this is another note to take care of. You can play with a different version of the Python. All right, so this is question number 1. So in tuple, we have all the values. It's immutable. We saw that. You can ask for the length, the element in X for a variable in X, the maximum and the minimum and so on. Okay, so tuple A is this, and you print tuple A. So let's see. Tuple A is this, and you print tuple A, of course, you get the same thing. And then tuple B is this. You print tuple B, you get that. And tuple C equal to tuple A plus tuple B. So this one plus this one. So let's try one of you. Okay, Ethan. Ethan Lim.
Yes, hi, Prof.
Okay. Tuple C, what do I get?
It's just A and B combined. So,
Oh, and then are they pointing in any way or is a separate thing?
no, it's a separate thing.
Okay, good. So there's a separate thing, copying this part from A, this part from B. Okay, then print tuple C, you will print out the whole thing. 14 in tuple A, what do I?
True.
True. 11 in tuple C,
False.
false. Tuple D equal to tuple B 0 times 4. Tuple B 0. This one.
Yeah, it's just 4 of the CS1010S.
Okay. So it's CS1010S, 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 CS1010S 4 times. And it is a string. So print tuple D 0. What do I get?
You just get that long string.
Huh?
Eh?
0.
Tuple D. Tuple D is not a tuple. It's not a tuple. It's a
It's a
string.
string.
So, is it an error? No.
No,
It's C.
it's C,
It's the first
yes.
character.
Yeah, what about this one?
It's everything else except for C.
Yeah. So you now notice that the tuple, a string behave like a tuple, just that the index it's counting character by character. Okay. Count equal to
Okay.
0. Count I in tuple A. How many tuple A is here?
Uh,
What is I?
I will be 0, 1, 2, and 3. So total.
No. Huh? Total. What is the total?
It's just the four of them add together.
Yeah. So it's 10 plus 12 plus 13 plus 14.
Yeah.
You have 49. Okay. Print maximum of this.
14.
Maximum is 14.
And
Maximum of minimum of this.
minimum is 10.
10. Okay. What about this? Maximum of tuple C. If I
Uh,
do this.
it's an error.
Yeah.
Because
Why is there
you
error?
cannot compare integer to string.
Okay. You cannot compare integer with string. It doesn't know. What about minimum?
Same error.
Okay. Same error. Thank you.
Okay, thank you.
Okay. Next one. Here. Let's try one of you. This is not in your question. Khalid.
Hello.
Hello. Yes. Okay, let's try this question. Term C is this. So this is what is this?
Tuple.
Tuple. Maximum of term C.
Uh, is it the BABB?
BABB. This one.
Yeah.
Why?
If I'm not wrong, the lowercase b is the out of all these is the highest, the ASCII code.
Okay, let's try. You can get ASCII code from here. ORD B is 98. ORD A, it's 97. So B is higher. ORD, what about character A? Capital A is 65 only. ORD, B, it's 66. So B is higher. So maximum, it's so B. But it's also a BAB. So why you choose this BABB?
Because he has more characters.
Yeah, so you compare one by one. This is called a lexicographical order. So B compare with B, so they are equal. A compare with A, they are equal. B compare with B, they are equal. This guy got empty anymore. This guy has a B, so this guy is larger. All right, so we got BABB. Okay, what about minimum?
Should be the capital AA.
Yeah, why?
It has the smallest ASCII code out of all.
Okay, so because ASCII code for AA, you saw it, it was a 65. 65. So it's the smallest among them. So 65. Okay, now A is 1, 2, 1, 2, 4, 5. B is that. So C equal to A plus B. What do you get? Kadip?
Uh, you get both tuples combined together.
Okay. And then D equal to A times 3.
You get the 1, 2, 4, 5 repeated 3 times.
Okay. The ID of D is somewhere in this location before. D equal to this one times 3 again.
You'll get the same output.
Get the same output.
Yeah.
What about the address? This is the address 52216. Will you think they will be the same address?
Honestly, not sure, but if I have to guess,
Okay.
I'll say different.
Yeah. So this A bracket is useless. This A, the parenthesis is means just A. But A times 3, so it's actually the same as this A times 3. So these two guys are actually the same statement. But one is done and then it's done the second time. So what we want to see is whether the ID still remains the same 5216. Oh, it's not. Okay. So actually, whenever you create a tuple, it's created differently. All right. So you honestly cannot tell. Yes, you can't tell, but now you know. Whenever you create a tuple, you create the same value of the tuple, you are actually destroying this guy and creating a new one. All right, Khalid. Okay.
Yep.
Okay. Next, E equal to A comma. Oh, there's now a comma here, because this parenthesis is useless. But this A comma means that you're putting the tuple A into a tuple. So it's a
You
tuple
get
of tuple.
you get a nested tuple. So like one tuple
Uh,
will be 1, 2, 4, 5. Then you have another tuple of 1, 2, 4, 5, and the third one.
okay, what's the length of this tuple? E. The length
3.
3. Okay. So you get 3, and they are all pointing to the same tuple. Now A is changed to 1, 2. What happened? A is changed to 1, 2.
You point to another tuple 1, 2.
What happened to this guy?
It'll still stay there because E is referencing it.
Yeah. Okay, so this guy is not a garbage. If it is a garbage, means that nobody pointing to him. But because someone is pointing to him, so this guy is not a garbage, and he has to stay. All right, so you create a 1, 2, and this 3 there remains. You print E, you are actually printing 3 times of the tuple. The length of A is now 2. The length of D is now this length. It's actually 12. Length of E is 3, as we saw. Okay, 1 in A, It's 1 in A.
True.
True. A in A.
False.
False. A in A.
False.
A in A.
False.
False. Because this parenthesis is useless.
Yeah.
This one, A in A.
True.
True. Because A is inside A, yes. What about A in this?
True.
True. Okay, minimum of A, it should be easy.
1.
1. Minimum of this,
1, 2. Like the tuple A itself.
hmm? 1, 2. Yes, because there's only one guy there. So
Yeah.
it just compared to itself. You print C, C is this guy. Okay, C is this guy. C from 1 onward. What is this?
It will be from 2 onwards. So like the
Okay.
number 2 onwards.
Okay, C is backward.
That one you just remove the last element, letter C.
This is from beginning till the end. Letter C. No. Let me try again. This is from 1 to that. This is
1 to B. 1 to the
1
letter.
to till the end. So remove the last guy, the C, yes. And this one,
You'll get it backwards in steps of 2. So you should get CA41.
CA41. Okay. Very good. 1 to 3.
You should get 24.
1 to 3. 1 to 3 means 1 and stop before 3. So
Yeah.
stop before 5, so 2, 4. What about this one? Print C8.
Index error.
Yeah, this one the index error because 8 it doesn't exist. What about this one? C8 colon.
Empty tuple.
Yeah, okay, we did this before. So now you see Tupper, you can see string, it will behave similarly. So string is like this, string until, right, this is from beginning to where and in step -1. So what is this?
It'll be backwards. So
Backwards.
FEDCBA.
Okay. This one? This is going backward. This is starting from,
You get the same thing.
you get the same thing. This one, we're going backward, starting from
You get A.
the first guy, so you get A. This one, start from the back, you end at the back.
Is it empty string?
Yeah, empty string, so nothing come out. You print this one,
F.
R, F.
The
Yes,
F.
only the one guy, the empty string just now. -8 colon, so starting from the way above, where's my
You get the
ST?
whole string.
Before the whole string until this, and then so you get the whole string. From beginning till -8, -1.
Empty string.
This one is from way before until, or from the, in a reverse order, so you get empty string. So you got nothing there. This one, 1 to 3. 1 to 3 means 1 and stop before 3. So you get nothing there. This one, 1 to 3. 1 to 3 means 1 and stop before 3. So you get 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop before 3. 1 to 3 means 1 and stop bef from way before until the last guy.
A, B, C, D, E.
Yeah. And the last one, this one is index error.
Index
Okay.
error.
All right. So this question 2. Okay, let's do question 2. This is easy. Write expression whose value will print out like the following. 1, 2, 3. So this is easy. You just write 1, 2, 3. You will print it out 1, 2, 3. What about next one? 1, this 2 and 3. I can't do anything because if I do this, I get this empty. I can only make it into a string to get this. The next one, I can do 1, 2, comma, and plus 3, comma. I will get it also. There are many ways that you can get this. So you can, of course, do this. You can get it the same. Oh, no, sorry. I have to have this to get this. Okay. And then the last one is 1, 2, 3, 4, 5, 6. So of course, 1, 2, not to forget that there's a comma for this guy. 3, 4. It's a singleton, so you need to have that. And then 5, 6. Okay. Yeah, this is not exciting. This question number 2 is a little bit ridiculous. All right, question number 3 is here. All right, you're supposed to write expression so that you can return 4. In this case, it's 4. When x is bounded to the following value. So this is the value. This guy is at position 0, 1, 2, 3. So print S3, then we get it. We get 4. The length of S is actually the whole thing, which is 7. Now you want to get this 7. How do I get 4? This is the first, it's 1 item, 2 item, 3 item, 4 item. So this tuple has 4 items. 4 is on the second item, which is index 1. And within index 1, there is the third item, which is index 2. So you get 1, 2. Okay. So 7, this one is 6, 5, 4. This one is 3, 2. This one is a 1. So you want to get this guy, which is the 1, 2. So this is the 1, 2. The length of T, it's the length of this guy, which is 4. The length of T1, 1 is here, is this guy, which is 6, 5, 4, which is the length is 3. Length of T2, which is this guy, T2. And the length of T3, T3 is this one, is a single number, so this guy will cause error. Right, so this is not possible. The last one, 7, 6, 5, 4, 3, 2, 1, looks like this. And the 4 is inside the, it is a little bit difficult to see, but you can see it in this picture. 4 is here, that's what you want. So it's the 1, 0, 2, 0, 1, 0, 2, 0. Okay, so you get 4. And the length of U is here, this guy, it's 3 only. Length of U1, which is this guy, is 2. Length of U10, this guy, is 4. Length of U102, U102, which is this one, is 1. And the last one, length of U100, 1, 0, 0, 1, 0, 0. It's nothing, so this is an error. Okay. All right, that's question number 3. Number 4, we have this this is the question I told you. You're forced to use Tupper, and we want to see how to do all these things. This is supposed to be better with the file processing, but anyhow, we're just trying this. Okay, here is what we have. This is not realistic, supposed to be in the file processing, but anyway, I just copy all this guy here. They're all here. And basically in NUS, there are a few components for each module. So the lecture component, the tutorial component, the lab component, the homework component, the preparation work component. Basically, this means 3 hours for the lecture, 2 hours for the tutorial, 1 hour for the lab, 3 hours for your homework, and this is estimate. And this is 3 hours for your self-preparation. So in total, in this case, you are doing 12 units. 1 MC in NUS, it's about 2.5 hours. So if you have a course of 4 MC, it's about 10 hours you have to spend per week on the course. You have a course for 5 MCs, then you will have to have 12.5 hours, all right, roughly speaking. That's what we allocate our time. So in general, when you're in NUS, you're taking 5 courses because each course is about 4 MCs. 4 MC is about 10 hours of work per week, and 5 courses means 50 hours, which is more than the usual working hour. The usual working hour is 40 hours per week. All right, so as a student, as a young, energetic guy, you can do a little bit more. So 5 courses is the norm. Okay, you're supposed to write this whole thing. We shall do it in a long-winded way, in the sense that we explore all the various possibilities. The first one is make empty schedule. So this is nothing spectacular. This is a simple thing. So let me just, so here are 3 courses that I make, 1010X, MA 1001 and MA something else. All right, so basically I have 3 courses. That's the name of the course and the units. So what I have is, it looks like this. All right. I have the 1010X, it's a name down there, and then there is a Tupper. So you can see that this is a kind of the derived data structure, right? Because you are using Tupper of Tupper. All right, in the Tupper, you link to another Tupper to keep this thing. You could have designed it such that you can keep this Tupper like this, and all these are just simply one number after another. In doing so, it may not be so explicitly that it's the unit. It's just like another entries in this. So there are always all these design choices that you have to make yourself. For us, in this case, we will prefer that the name and the units are separated into 2 parts. The name can be kept in the first entry. The units can be kept as a separate tuple. Right, in this case, once you have decided on that, for example, here, get the module code become here cost 0. Get the module units become cost 1. Instead of cost 1, 2, 3, 4, 5. Because the design is such that it looks like this. A tuple inside there got 2 entries. The first entry is the name, the module code, or more than the name, module code. And the second one is the module units. All right, so it's done in this manner. Okay, of course, this is only one design possible. You can have many other ways of designing this. All right, so we have 3 courses. Now, we want to make empty schedule. So how does it look like? Empty schedule. This one should be easy, so I'll just give it to you. All right, these are just written empty. This is A. And the time, it's O of what? In this case, it's nothing. You just return this guy, right? And you cost you only a constant time. And also space, you don't use anything. You return this empty, so it's a constant. Okay. So part A, it's a constant. Order of growth in time and space. Okay, next, you add a class, add cost, and a schedule. So basically, a cost looks like what just now you saw. All right, this is a cost. Okay, this is another cost, this is another cost. So I want to take one cost and add it to my schedule. So how do I do that? So define, add, in this case called class, cost, schedule. Okay, so let's try. Can you post your answer in the chat box and then let me take a look? Oh, by the way, there was a question just now. Okay, let me see this one. Okay, okay. All right, first of all, Sumi Lee, you cannot make schedule in there empty. The schedule is already given. All right, the schedule is a parameter. So when does this say write a function add clause when the given class and a schedule is given. Return a new schedule including the new class. Right, you should not make schedule inside this thing. You can only add cost. So Isaac Lim, the straightforward one is like this. So let me just copy it. Right, you just take the schedule and add the cost there. If you do this, there is one thing that we probably should check is that you do not want your schedule to be duplicated with courses. So maybe this is not good enough. Of course, in the question itself doesn't tell you that, but we can also make our exercise more meaningful. That this may result in a schedule that it's duplicated with courses. Right? You can call this many times. You return the schedule with the same course. So we don't like this. So if we want to avoid that, we probably should check if course in the schedule, then we probably return just the schedule. That means we don't add the course. Otherwise, we know that the cost is not in the schedule. We return the cost with the schedule like this. Or you can do it the other way also. This plus schedule. Okay, so either way will work. Remember that you need to have a comma here, because if you don't have a comma, this will be taken as the same as this, which is wrong. Okay, so we needed a comma here. Now, if you do this, Isaac Lam, what is the time complexity for this? This is B.
Hello.
Louder.
I think the time complexity is ON, because you have to make a whole new tuple to return.
Okay, yeah, you have to make a new tuple here. So what is N then?
N is the length of schedule.
Okay. All right. Louder. I cannot hear you a little bit. But all right. So you needed the time is ON and the space is what? O what?
Also ON.
ON. Yeah. Where N is the number of causes. Okay. All right. So this is one version. Let's see. Anyone does okay. All of you are very careful with with this. Well, let me give you a dumb solution. A dumb instead, it's a recursion. It's just only for practice, for purposes of our learning. This is really dumb, but you will know why it's dumb. B, version 2 is a recursion. Looks like this. Define add cost, same. If the schedule is empty, we know that we can simply add the cost. All right. Correct. Or I should, if the schedule is empty, maybe a more meaningful thing will be make schedule or it's already empty. Okay, so the schedule is empty. Then you return this cost with this. Otherwise, if the cost is the same as the first cost, all right, then I will return the schedule because it's the same as here. Otherwise, meaning that the first cost that we are looking at is not the cost that we are adding. But who knows? Maybe subsequently there's costs that it appear in the subsequent part. So we need to keep this cost and we recursively call this routine with this cost and the schedule starting from the second one onward. All right, so this is okay, right? Now, what is the time and space? Let's try. RJ.
This is recursion, right?
As I say, it's a dumb thing, so you shouldn't guess that what is the time and space.
I would say is it O(n) squared?
Yep. N squared.
Yeah.
And space?
Base is that. So space is the depth, right? Is it also O(n) squared?
Yeah. Okay, so there's a defer. What is this O(n) square? We know shortly. We can see it now. You see, you are keeping this guy. You have this add, which is going to be defer, and therefore there's you keeping this cost, and you're creating a schedule. You're paying the n-1 here, and this n-1 goes in, and you create another one. You have n-2. And so on. So the space stack up and you are getting O(n) square. Each time it's n-1, n-2, and so on. And as a result, because of the space also that, the time is going to be at least the same as the space or more. In this case, it's the same because you pay the same time to make the copy. All right, so this is, yes,
The space is also n squared because it's creating new tuples, right?
it's because it's what?
Is it creating new tuples?
Yeah,
instead of
it's creating a
reducing?
new tuple. It's schedule.
Okay.
Yeah. Right. So if you run this thing, you can run this thing. Oh, okay, let's try. Let's try to run this thing here. Not here. So make empty schedule. So I have an empty schedule. All right, I have an empty schedule. This schedule done. That's me. Okay, I add a class. Because it's empty, so immediately I just add. And I add another class. Now I have to do recursion. A little bit messy now. This is not so obvious. Maybe we should make many more coils. And then the picture will look very Strange, but anyway. All right, you should try this yourself. What do I call them? XXX. One, two. The schedule is added at the end, so we can try. Okay, it's going to be messy. The same cost, this should not be added. Okay, I have no eye to see this. It's it should be, look at this. They it should be recursive as such that you see the stacking of things. All right, I don't want to play with this anymore. Okay, I want to do C. Let's see. Write a function that compute the total number of units in a specific schedule. Okay, so this should be easy. Can I see your code? Are there any advantage for the dumb version of 2? Or maybe we can add debug code. Okay, there's no reason for me the dumb version. Uh, all right, we do some of this dumb stuff. It's just to learn something, but there is no practical use of it. As far as I don't recall anything that useful. All right, I guess this question, it's there to hopefully you learn your lessons that you should try not to write much code, but use some of these things. Basically, you want to reuse the module. Okay, so here is what I have. This is not particularly difficult. So maybe I remove some of them first. All right, so I have 3 courses, and each course it's these 3 courses 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this guy has 12 units. This guy 2, 4, 6, 8, 10. So this guy is 10. This guy is 2, 2, 6, 7. So for myself, with these 3 courses, I should get 29. So this total schedule unit should be 29. Let's see. $29. Okay. So how does this work? There is no, I guess it's not much different from all the rest of you. So, this is my C. I do get unit by get module total unit. I use this guy, which is the sum of all these numbers. So you give me a cost, I can get this. So if you give me a schedule, I initialize my total to be 0. And then for each cost in my schedule, I go and get units, which is calling this routine. Of course, you can do this thing directly in here. So get module units. Yeah, which is here. So if you want, you can also replace this. And don't want this too. Still get 29. Okay. All right. So it's basically that. And I print it. That's all. Of course, the question is, what is the time and space complexity? Time and space O n and O1. All right. O(n) is because where n is the number of courses in the schedule. You just go through the courses in the schedule. Yes. And O1 because you don't have anything other than this course. So, and a total. So it's O. The space is O1. Okay. All right. Part D. Write a function drop class. Okay, let me see yours in the chat box. Router sketch. Oh, okay. So I do see something similar to recursion now. Yeah. Okay. So let's try. Here's what I have. Let's do one at a time. So this is a recursion. E. All right. So if the schedule is empty, then nothing to drop. You just return empty. Otherwise, you check whether the schedule, the first course, is the same as the course you want to drop. If it is, you can drop class, schedule from that one onward, the course. All right. Actually, this. Why do I do this? Oh, this is a little bit redundant. I could have just simply written schedule 1, I think. One onward. Okay. And otherwise, I keep that course and drop the course from 1 onward. Okay. So what is the time and space for this guy? Again, you see that you are creating this most expensive part. You keep one and you have to stack up this plus and you have to recursively do this. In the recursion of doing this, you are actually doing this tuple creation of n minus 1. So the time complexity of this guy is the time that you need is equal to, you can say it's 1 plus 1 plus is O of 1 plus O of 1 for checking, and then coming to here, plus, and you pay for n minus 1, okay, to create this guy. And then you call it, and you call it with how much time? It's n minus 1, okay. Then there's this trick in the computer science, this is called, or in mathematics, this is called telescoping. N minus 1 plus, what is this guy? This guy is simply substituting into, take n minus 1 is 1, 1, n minus 2 plus t n minus 2. So you will get O1 plus O1 plus O n minus 2 now plus O plus t n minus 2. Okay, then you keep doing this thing, you will get all this thing will be the same, and this guy got expanded into this thing with n replaced with n minus 2, so this becomes n minus 3, n minus 3. So I should say this is n minus 3, and this is n minus 3. So you can see that other than O1, 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 I have On minus 1, On minus 2, On minus 3, and all the way until On minus n plus 1. So this is again the same as T n is equal to O of, all this O1 sum up will become On. So there's a On term plus the rest is O of n minus 1 plus O of n minus 2 plus O of n minus 3 and so on. All right, so this is actually in this way you can see this is O of n squared. Okay, where n is the number of courses in the schedule. Okay, so this is n squared times, and the space is also the same because this guy is actually also represented here as the size of it that you use to create. And so this is the time, it's On squared, and space is On squared, where n is the number of courses in the schedule. Okay, so this is one version. And I think I also see another version. Let me just give it to you. The version 2. All right. Drop class schedule course. New schedule equal to make empty one. So you get a new schedule, and you are supposed to return the new schedule. For the item in, so this is iterative. This is a recursive. For item in schedule, if the item is the same as the course, you just skip that course. Otherwise, you add that course into the new schedule. And this is what you are basically going through the schedule and drop the one that you don't want, and the rest you keep. So this one easy to analyze because you're just going through the courses one after another, and you just drop one. And this one it's creating it, the tuple, but unfortunately the tuple that you create increase in length of 1, 2, 3 until n minus 1. So this is again another stupid thing because the tuple is immutable, and therefore you're paying it, even though this is iterative, and you would think that you want to get On, but you can't. So the time is still On squared because you are creating this new schedule of size 1, size 2, size 3, and so on. Okay, and the space, it's what is the space? This is an interesting one. Let's try one of you. 浮乘以
I think the space is ON
why?
because you only make one new schedule.
What? Sorry?
Because you make one new schedule.
I make one new schedule, but actually I make many of them. So what is happening? I'm making many version, right? I'm making one with this size 1, size 2, size 3.
So
That's
it's,
huh?
so it's ON square, is it? Because you keep making a new one every time you add.
Yeah, actually this is a reusing of space. Right? Because it's the moment that you change from 2 items to 3 items, the 2 items guy is become a garbage. And the garbage will be collected and you are not paying for it anymore. So you pay for the longest, which is n minus 1 and the most, or n if the cost doesn't exist in there. So you're reusing the space, and therefore you are right that Fu Chen that this is O of n. This is the largest length of this schedule, right? Where n is the length of the courses, where n is the number of courses. There's a question in the chat box. Why is the space of the recursion version O n squared then? Why is this O n squared? Because this one, it's existed for every recursion call. This one is stacked on top of each other. This one is overwriting each other. You see the difference? So this become an interesting thing that we actually reusing of space. Space is something which you can reuse. If it is garbage, it's no longer counted. But time can never be reused. Time is just like money. Once you spend, it's gone. Right? But space is something which you can reuse. This thing should stick to you. The time is always larger than the space. And the time once it's spent is spent, but space can be reused. Right? Do I answer you, Chong Kai Yang? Kai Yang, are you there? Okay. Yes. All right, so you have to be careful. So we do learn things by giving ourselves of things to do, and then through that we learn. Okay, so that is the version for iterative. Yeah.
I have a question for the job class, the recursive version. Just now when you explain the time for the elif schedule 0 equal cost you put it as the time as O1. Shouldn't this be ON minus 1? Because you have to, in the worst case, you will have to create a new schedule minusing the first
Can you refer to which line you're talking about?
line 72 and 73.
72, this one.
Yes. Because
And
in the worst case, this is true schedule 1, schedule in starting second element onwards. And thus this one will create, isn't this an ON minus 1 time?
this is ON minus 1 time. Yes. What is the problem?
No, cause just now you put as O1 time, so just want to just
Yeah.
wanted to clarify.
Oh, no. I put O1 because I do this checking only.
Oh.
But once I hit here, I'm done. No more recursion.
Oh, okay.
Okay?
Okay.
I pay
Understand.
for this else if statement only. I pay for this if statement. I didn't pay for the return. If I pay for the return, I don't come back anymore.
Okay. Understand.
Okay.
Thank you.
Welcome. Now we are at D. Okay. Credit limit. So you have a schedule, you have a maximum credit limit, and you have to remove classes. You cannot take too many. So can I see your posting? Okay. All right. So I see two different ways of doing it. One is that you keep taking courses until you hit the limit, then you stop. The other way is keep dropping the course. You drop a class and you check whether the credit limit is enough or not. If not enough, you drop some more. Okay. So let me just give you one way here. This is one way. First, I go and calculate the total unit I have, but I have to make sure I have this maximum that I can take. So I calculate my total. If my total is larger than the credit I can have, I take away one class. Actually, this is a bad habit now. I should have dropped the class. Okay, maybe I should drop the class and calculate the total again. But I lazy. I just do the minus from this unit and become my total. And my schedule is the first one is drop. Then I I repeat this calculation. I repeat this checking because the calculated already total is there. So and keep dropping. So this is the keep dropping one. I see some of you do it by keep adding. Okay, so they are the possible. The more interesting. Oh, okay. Maybe what is this time complexity here? Let's see. Isaac Lam, you have the same solution. So what is the time complexity? Yours is better in that you reuse the routine, you drop class. Okay. So you are learning, you're doing things in the proper way. That you reuse some of the routine, whereas this is bad. Okay. But they are the same logic, so they should have the same complexity. So what is yours, Isaac Lam?
Okay, if I'm using drop class,
Louder.
since I'm using the drop class space complexity and time complexity, it's the one I'm using. Is it n? Like both are time and space are n.
Okay, this is a little bit tricky now. So I see your point. Because you're using the drop class module, this guy in the worst case can be on square and on space. So space is not an issue because this space can be reused. But you're calling this drop class n times potentially. So you may end up with n cubed. All right. But on the other hand, it depends on which class you drop. You could be dropping the front, then you may not need to go through on square. You may just simply drop and take the rest. So one time is counting. Okay, so it's still possible. But on the other hand, now it become mine is clearer. I don't reuse that, so I'm not at the mercy of this guy. I'm just doing this one. It's linear time, and I just subtract. It's again constant. I take this. It's linear time. So I do this thing n times. So I will be paying on square. So mine is for sure. The time is on square at most. Yours become at the mercy of this drop class. And because this guy is n square, you will do it n times, you will n cube. But on the other hand, you must see, this version will have to kena that, whereas this version will be able to hit here and quickly return. So this may be a better version for you than this one. So now you see that depending on how this one turned out to be better than this iterative. somehow because this recursion will be quickly get out of the recursion. Anyhow, if you have doubt on this, you should ponder about it after this class. Anyway, this is mine is clear, it's ON square, and the space is also clear. My space is only taking this schedule, dropping one class. And because I reuse a space, so I don't need more than ON. Okay. So, Isaac Lam, are we in sync?
Yes.
Okay. All right. So, but this is not an interesting question. Actually, the interesting question is the last one. Implement an improved version of credit limit that will return a schedule with a total number of units that is less than or equal to maximum credit, but with the maximum number of classes. What is the order of it? And what's basically, for example, I have an example here. Okay, maybe the credit unit is something like 10, 10, 10, 11, 12, 12. So credit limit, let's say you have 41. So your solution should be 10, 10, 10, 11. Okay, to 4 courses with 41 limits. Okay, you can take 4 courses. All right. On the other hand, if you choose 11, 12, 12, you can only kena 3 courses only with 35 credit. So, solution to meet the credit limit is if you have a solution for this, for example, if you take from the back, if your algorithm take this from the back, once you hit here, you got 35, you cannot add a 10 because you will get 45. So you ended up with 3 courses. On the other hand, the solution is you will go from the front, add 1, add 1, add 1, add 1, you can get 4 courses. Okay, so the last part is to ask you to write a routine to do this. How should you write your routine? This one is anyhow dropping, which may kena this kind of bad solution of 3. So we must have a way systematically to take things or drop things. So how would you do that? Can I see? Oh, somebody do sorting. Wow. Okay, that's why now I see why you have a question about which one is a stable sort. All right, in place sort is not necessarily a stable sort. There's no in place means that you are reusing the space, but things can be jumbled up if you are not careful with the in place. So I cannot ascertain in place equivalence to stable. Okay, there was a question much earlier. Okay. All right, so most of you do sorting. You sort it and then you take the causes from the smallest to the largest units. Am I right? All right, so here's the logic. Sort the schedule with smaller credit unit cost in front. Okay. And larger credit unit costs at the back of the schedule. All right. Then go into a loop to take courses one by one until we are about to reach the credit limit. All right, not exceeding, but about to reach. That means that taking yet another course will exceed the credit limit. Okay, so we do this. All right, so this is adding. Here is another one without sorting. So let me just give it to you. Basically, I take this schedule. I want to modify it to be more clever. And how do I do this? I want to replace this part. All right, here is I sort and then I take the smallest all the way. Here is I don't sort, but I have this. And I do my while in this manner. Okay, so my total greater than this maximum credit, I will take my largest so far is 0. Index is 0. For I in the schedule, basically I want to find the largest guy, all right, that I want to remove. So my total will be taking away that particular schedule. And my new schedule will be from the beginning until before him plus after him till the end is my schedule. And once I'm done with this loop, I technically have dropped one class. And at this moment, I should check whether my total is still larger than credit limit. If I no longer larger than credit limit, I can return. That means I'm done. Otherwise, I will continue to do this. Each time I do this, I'm finding the largest to drop. Okay, I don't do sorting. So sorting it's not necessarily a must here. I can do it without it. I basically pay the price to look through the item for the largest. So in the worst case, this routine will take me at least n round, and therefore without sorting, and this guard is going to take me also n. So without sorting, I will have to pay n square in a way here. Alright. While sorting actually pay for only n log n, because you sort it's taking n log n time. While without sorting, doing one by one, it's on times on, which is on squared. So who is better? So here it's depend. Alright, if you just have a few causes to drop, so your on square could just be O times n times 3 causes, it means 3 times, so it's still linear. So usually sorting is costly. We try not to sort if we don't have to. In this case, you are basically finding the largest to drop. And again, it go to the question about frequency or the kind of thing that you must do. In this case, I don't have to rely on the sorting. Sorting is just a convenient thing for me to drop one after another. If I willing to go through dropping one at a time, by going through finding the largest and then drop it, it will still achieve my goal. So what is the
is it not ON?
yes? Huh?
Is it not ON for the
This one ON?
yeah, inside the loop is should be ON, right?
Yeah, but then I have to create this tupper is ON, right? And
Yeah, so
I
it's
do
ON
this
and
thing.
ON.
Yeah, which is ON square, right?
But the sorting is also ON square.
No, sorting is ON log n. Oh, you haven't done sorting. Sorting is n log n.
No, but inside it's only n log n for the first line. But then when you remove and create a new array, it's still n square.
Oh, yeah. Okay. Yeah, that's true. Okay, sorting is in the front is ON log n. At the back, you remove one. Yeah, so it's ON square. So, yes. Okay, yes. Right. But there is a hanging question here. There is a question for you to think about. How can you be sure this is correct? That means your approach is giving the answer as needed. This is in the topic of proof of correctness. All right, and I will do a little bit of that for you in the next review. You are not needed in this class. Proof of correctness is usually tough. Why do I have that? Let me just pull out this. Here. You learn to write code. We started out with anyhow writing the code. We just write the code. And we learn about writing better code, making commands, use meaningful variables. And then we talk about time and space complexity. We write efficient code. Then we talk about writing the correct code. We got proof, which is more in your future course. And this is not needed in this class, but I want to show it to you to complete the picture. That's what your learning journey. You have written some code somehow it come up from you as a computational thinking. You know how to do it. And after you have your first version, you usually can then class it, write a better one, making commands, making meaningful variables, and so on. A good code, it's not just beautifully looking, but it should be efficient. That's the next step. Therefore, we talk about time and space complexity, or you change your data structure to get a better time and space complexity. And once you have done this, for example, I've done it here. Okay, how do I know that this is correct? And there are always why this is computer science is linked heavily to mathematics, because you can actually formally prove that this is correct. How? I give you the hint here. Because if this is not correct, meaning that by contradiction you have another better solution, and that better solutions I will write it out next round. To that solution is with A, B, C, D. Then I will be able to replace one of the causes in there with one of the smaller value if we are not identical. Then I will be able to improve. And the contradiction will allow me to say that my code is correct. I will do that in a better way next week. We have a long day already. All right. All right. So this is a journey that you have gone through. And this part of the thing, it's in another course. Okay. I forgot to do all these other things. Okay. Okay. All right, I'm done with the recitation. Any question? So this is always encouraged. You don't just look at the recitation as it is, but create new question yourself so that you have a good practice and make a lot of possibility. And this is what we learn always. You know all the options that are available to you, and who knows, some of these options are actually used in our assessment as well. So creating prompts is also a good thing to do, right? So looking at this, how can you change it? And in fact, if you have started your preparation for midterm, you will know that some of the questions are actually recasting of the same question, just make it a different version with a different assumption or with slightly different objective, and that become a new question. Right, like here, you should ask the question about what happens if this whole thing is implemented in list, and what will be the changes of the time complexity in all these various module that you needed to write. Okay. Are you okay? If okay, give me a check, and otherwise you can ask question in the chat box. Okay. All right. If no, then we call it a day. Bye-bye. Oh, I actually did the midterm here. Please check it out. For those of you who are still in NS, if you do have duty, you better tell me. Okay, if not, then you can quit. Oh, I have another question. I got a question down here. Let me see. Oh, have a nice weekend. Tomorrow I have to teach again. Bye-bye. Okay, I quit.